Hello everyone, Mrs. Hanson back again. Hope you found a little bit of rest and are back to talk a little bit about Sn2 stereochemistry, bimolecular nucleophilic substitution. So what does the observed stereochemistry tell us about the mechanism of an Sn2 bimolecular collision? And let's just keep practicing until we understand some vocabulary. I notice this is what I'm going to call my substrate. The substrate is the alkyl halide in this example. The substrate contains the leaving group. And our leaving group is identified here as the bromide. In this example, SH negative is the nucleophile, which we understand means seeks an electrophile, seeks the positive carbon. The nucleophile, SH negative, now remember this is all electron rich on that sulfur. There's 3 sets of dots there. The substrate has a chiral carbon. Doesn't have to for this particular mechanism to work, but this is how we studied the mechanism. We used a chiral carbon and examined the outcome. When an alpha position is a chiral center, notice this alpha carbon, alpha is attached to the leaving group, we see a change in the configuration 100% of the time. And there's an explanation for that. The nucleophile attacks the electrophilic carbon in a backdoor attack. 100% of the time, and we form a transition state. And if I may, I'm going to draw the transition state on the arrow so you could see that it's not a reactant, not a product, but it's going to form at the top of the energy barrier. Here is our chiral carbon center, and the transition state would show the bromine bonds breaking because the leaving group is leaving, and in the exact same plane, the nucleophile has bonds forming. So I'm going to label that. These are the bonds that are breaking as the leaving group is leaving. These are the bonds that are forming as the nucleophile adds on. And of course that carbon would also still have its hydrogen, its methyl group, and its ethyl group still attached. And the transition state is placed inside of a bracket, and you see kind of this double dagger up there to show it's the transition state. Now remember, on the energy diagram, we would have a reactant turning to product. The transition state is at the top of the activation energy hill. So this right here is the top of the hill. That's the transition state, where bonds are breaking and new bonds are forming. It is not an intermediate. It cannot be isolated. Intermediates can be isolated. Those are what we will learn. Those are formed and then immediately used. That's a 100% intermediate. But here, 100% inversion of the chiral center is going to occur. So let's go back and kind of review chirality. Chirality says I have a carbon that has 4 unique attachments. Priority 1 is given to the highest atomic number. Priority 1 here is the bromine. Priority 2 would be the carbon that's attached to most carbon, and priority 3 is the carbon attached to least carbon, so ethyl, then methyl. When I spin my priorities, I get a clockwise rotation. However, notice that the hydrogen is a wedge, which is exactly the opposite of where I want it. So we've learned to just go around the other side of the molecule and flip your direction. You get a counterclockwise spin, and that's the S configuration for that compound. The highest priority is now the thiol group, the sulfur, followed by the ethyl, then the methyl. This is now spinning in a counterclockwise configuration, but the hydrogen is the wedge, so we just get up and walk around and look from the opposite side. And you flip the rotation. This is a clockwise configuration. It is now the R stereoisomer. 100% of the time you have inversion of the configuration of a chiral carbon. S will 100 convert to R and vice versa. And the reason we can say that this mechanism is working in this way is based on that observation, that in the same plane, in a backdoor attack, this electrophilic carbon is getting attacked from the nucleophile in the same plane as the bromide or the leaving group is leaving. That transition state helps to explain the chirality inversion. And that's what I've drawn for you here. The transition state, notice that these are in the same plane. The nucleophile attacks the electrophilic carbon in the same plane as the leaving group leaves. That's the bonds breaking of the leaving group. This is the bonds forming of the new nucleophile. And the transition state gets this double dagger sign right there. This is called a backdoor attack, where I have the electrophilic carbon gets attacked from the nucleophile exactly in the same plane but opposite direction, forcing the leaving group to leave. All right, so let's consider some of those as we work some practices. Here I have an R configuration of 2-bromobutane. Let's verify just to practice. The H would be a dash, just like we want it. Highest priority would be the bromine. Second priority would be the ethyl. Third priority would be the methyl. When I spin, that is a clockwise rotation. So yep, that's an R, 2-bromobutane. In a bimolecular collision, this strong nucleophile is hydroxide. The hydroxide is going to attack the electrophilic carbon in the opposite plane, right? So in the opposite direction of where the bromine is attached. So it comes in from behind, a backdoor attack. And that forces the leaving group to leave. And so now when I redraw, the bromine has left and the hydroxyl group has taken its place, and we have an inversion of the configuration. So let's verify that that indeed has happened. Top priority is number 1. Here's 2. Here's 3. When I spin, I have a clockwise rotation, but the hydrogen is a wedge, and so we flip and we get a counterclockwise. This is now the S configuration. At carbon number 2, we have an alcohol group now. We've had a substitution where alkyl halide has turned into an alcohol. A substitution reaction, changing one functional group into another. And the nucleophile you select determines what new functional group will replace the original halogen. So 100% inversion, just to clean that up. If we started with a dash, you turn it to a wedge. If you start with a wedge, you turn it to a dash. Backdoor attack all the time, 100% inversion. And that's exactly what we drew. We drew the opposite configuration. Let's practice drawing some of these. This is an example homework question. Let's draw the products for this Sn2 reaction. I'll try letter A. It says S2-chloropentane. All right, so let's draw a 5-carbon ring or 5-carbon chain. 1, 2, 3, 4, 5. I'm going to make the chlorine a dash and then just check. I honestly don't know if that's going to be S or R until I check. Priority number 1 is the chlorine. Priority number 2 is the longer carbon chain. Priority 3 is the shorter carbon chain. And again, I see a hydrogen as a wedge. So when I spin, it is clockwise, but I have to flip the direction. So I'm on the opposite side of the molecule, making the hydrogen turn into a dash. That turns counterclockwise. Look at that, I got lucky. That's an S configuration. So there's our S2-chloropentane. Sitting on the arrow is the nucleophile. It says sodium thiosulfide, thiol group right here. SH negative is going to be your nucleophile. So that will be the functional group that we exchange the chlorine into. Let's remember the mechanism. The nucleophile attacks the electrophilic carbon, forcing the leaving group to leave. And when that occurs, we have 100% inversion, where the nucleophile is now the functional group and it turns into the opposite configuration. Let's verify. Priority 1, 2, 3. The hydrogen is the dash. Yay. And so we get a clockwise spin. No need to flip because the hydrogen is in the back, and that is indeed an R configuration. 100% inversion has occurred. And you'll always hear that as a backdoor attack, meaning that the electrophilic carbon right here, and I just think about, is being attacked from the opposite side of where the leaving group is. It pushes the leaving group right out. How about letter B? R 3-iodohexane. All right, let's see. 1, 2, 3, 4, 5, 6. And on carbon 3, we have an iodo. I'm going to make it a wedge without really knowing. I'll just check it. Priority number 1 is to the iodine. Priority 2 would be to the longer carbon chain. Then priority 3, hydrogen is in the back. So that's spinning 1, 2, 3. That's counterclockwise. That's an S configuration. Darn it. But there's no way to know for sure. I just had to guess. 1, 2, 3, 4, 5, 6. If the wedge didn't work, it must be the dash. That's my starting compound. This would be the R configuration. So that's just really draw it and just check which one is going to be the R and the S. Now I've confirmed the R configuration places the iodine as a dash. Notice my nucleophile now is another halogen. So the nucleophile is chloride. I'm exchanging one halogen into the next. The chloride backdoor attacks the iodide, forcing the leaving group to leave. And when it does so, here's 1, 2, 3, 4, 5, 6. On carbon number 3, we have an inversion where now we would have S configuration. This would be called S3-chlorohexane, a 100% inversion. Let's take a look at letter C while we're practicing. Give myself a little more room. Bromohexane. 1, 2, 3, 4, 5, 6. At carbon number 2 is an R configuration. I'll make it a wedge and just simply check my work. There's a 6 carbon chain. At carbon number 2 is a bromine. Highest priority would be to the bromine. Second priority would be the carbon attached to more carbon. Third priority is the carbon attached to the least amount of carbon. Hydrogen is the dash, just like we want it to be. This is spinning in a clockwise configuration. So yes, this is indeed the R configuration. Sitting on the arrow as your nucleophile is the cyanide, Cn negative. Your nucleophile has the formal charge on the carbon, Cn. Now just remember what that looks like. C triple bond N, carbon with its formal charge of -1, cyanide. We have a substitution occurring, meaning 1, 2, 3, 4, 5, 6. At carbon number 2, we've created a new functional group of Cn, and it would now have the S configuration. And you've got that. You have one more to try on your own in letter D. Let's think about the kinetics of a bimolecular collision. The alkyl groups that are branching out from the alpha and beta positions can serve to hinder or slow down the rate of a reaction. Let's suppose we have a methyl bromide as our substrate, a methyl bromide, and we have a nucleophile that wants to attack this electrophilic carbon. Remind yourself why it's electrophilic, the polarity of that bond, the withdrawal, the inductive effect of the bromide is making this a beautiful target for a nucleophile. The nucleophile has a very easy time when I have a primary substrate of reaching in to find that electrophilic carbon. But what happens if I start to take that electrophilic carbon and start burying it behind big bulky groups, such as a methane on each one, right? Notice that these are all CH3 groups. And just to emphasize how buried that electrophilic carbon is becoming. So with this example, this is called a tertiary alkyl halide. You notice how this carbon in the center, which is our target, is unhindered in a methyl group, but it's very sterically hindered with a tertiary substrate. So much so that by the time I have a tertiary alkyl substrate, that this carbon is so protected, so sterically hindered, that a nucleophile does not have the ability to get in there and attack the electrophilic carbon. So you can see that substitution reactions do not occur at all, and we would only have elimination occur at this point. So if I want to favor substitution, I want to have an electrophilic carbon that's not being hidden. Think about it as a primary alkyl halide, methyl, and even if I could have just one here as an ethyl, it's still a primary alkyl halide. But now I have a secondary alkyl halide, and look at the significant change of rate. And a tertiary alkyl halide, the rate is so slow that no appreciable product would form at all. And that's even true as you consider in the beta position. Each time I add more bulk to the beta position, the rate significantly slows as well. So to promote collisions, we need an unhindered target. And that's what this is reminding us in terms of the energy. It takes a whole lot of energy to try to create a transition state when that carbon is buried and protected by other alkyl groups. So notice this feature. The rate of the chemical reaction is measured by the activation energy. The lower the activation energy, the faster the kinetics. And in terms of thermodynamics, you're looking at this particular amount of energy, the difference between reactants and products. And so this is a favorable reaction both in terms of kinetics, because it has a low activation energy, and it's favored thermodynamic because it has an exothermic reaction. Whoops, I just hit that with my hand, sorry. The exothermic reaction. So this is favored in terms of both kinetics and thermodynamics. Whereas by the time you have a tertiary alkyl halide, tertiary alkyl halides have such a large activation energy that slows down the kinetics. And in terms of thermodynamics, you don't have much of a difference between reactants and products. So that's thermochemically not favored. And that's what they're showing you on this slide. When you start to compare activation energy, this would be a methyl substrate, where you would have your bromine just simply attached to all hydrogens there. This is a nice, easy target to try to get to. Here's a primary substrate, meaning that the carbon is attached to just one other carbon, a primary substrate, and still giving you an easy chance to get in there. But by the time you have a secondary or a tertiary substrate, the kinetics is slowed down tremendously. That this becomes more and more sterically hindered. Notice that the activation energy increases significantly by second and tertiary. Let's just think about an example of neopentyl bromide. 1, 2, 3, 4, 5 carbons. In a neo position, the beta carbon has 3 methyl groups hanging off of it. So a common name of neopentyl bromide. You could also name this as, it would be called an IUPAC 2,2-dimethyl. I'd have to alphabetize 1-bromo 2,2-dimethyl propane. That would be its IUPAC name. But a common name is neopentyl bromide. Would you predict this to have a mechanism by Sn2 reaction? And would it be fast or slow, and why? And just really bringing that previous slide back, here's your electrophilic carbon. This is your target. This is your big, bulky group. In the transition state, this big bulky group is actually hindering the ability of the nucleophile to have a successful collision and force the leaving group to leave. The big bulky group will slow down the kinetics. This most likely will occur at a very slow rate, probably so slow it wouldn't even produce any kind of an appreciable amount of product. So steric hindrance of the alpha carbon should be considered if you'd like to have a substitution reaction. Make sure the alpha carbon is not behind big bulky groups. We're going to have some homework that has you just practicing drawing transition states, so I just thought I would model some of those. We can see this is a nucleophilic substitution. Here I notice that a chlorine functional group has turned into a thiol functional group. S is in thiol. And so the transition state, here is your alpha carbon. The nucleophile, SH, is very electron rich. It is going to attack on the opposite configuration and the leaving group leave. All right, so there's our mechanism. Here's your alpha carbon. It has a leaving group of chlorine, and in the same but opposite side, you have your nucleophile attaching. So here's the point of bonds forming, and there are the bonds breaking of the leaving group leaves. Those are why they're dashed. Now you've got other attachments here. There's 2 hydrogens, and you have another carbon down here. Then you see this in a bracket, and you see it with a double dagger sign there. That would represent the transition state of this bimolecular collision. Shall we try some more? Again, I'm just picking from your homework. This is a substitution reaction where an alkyl halide has turned into an alcohol. We have changed functional groups. Selection of your nucleophile is critical. If you want to create an alcohol, you better pick a nucleophile that gives you the alcohol, the OH. Here is the alpha carbon. So just thinking about what's happening, we have a backdoor attack and the leaving group leaves. Start by drawing your alpha carbon, and in the same plane, your leaving group is leaving while the nucleophile is attaching. The other 3 bonds, this guy here is attached to 2 other hydrogens, so I'll just draw them on top. And the carbon is also leading down to a cyclohexane. And this would all get placed in a bracket with a double dagger sign there to represent the transition state where bonds are breaking and new bonds are forming. The leaving group leaves as the nucleophile attaches. I don't have enough carbons in that, do I? I just realized that this is a carbon, then leads down to a cyclohexane. I just want to make sure I get this carbon in my picture. That would be this carbon here. How about this guy? Here's your alpha. This is going to create an ester. When I look at my substitution, the alkyl halide has been turned into an ester, so the nucleophile I select had better contained those functional groups that I want. So the oxide is going to attack from the back door. So just draw your alpha carbon. You're going to draw in the same plane the leaving group leaving as the nucleophile attaches. And what's left? This carbon also has 2 hydrogens, and it leads out to 2 more carbons. And we'll place that in a bracket and give it a double dagger sign. There's your transition state of a backdoor attack, 100% inversion if it's a chiral carbon. Let's also talk about the nucleophilic strength and solvent effects in a substitution reaction. Begin by defining the term nucleophilicity. When I define nucleophilicity, it's the rate at which a nucleophile will attack. The stronger the nucleophile, the faster the kinetics. And if I have a weak nucleophile, I'm going to have a relatively slow bimolecular collision. If the goal of the collision is to force the leaving group to leave, you want that to be powerful enough to kick out the leaving group. We need a strong nucleophile to have a fast kinetics. Well, what makes a good nucleophile? And that goes back to reviewing chapter 6 in section 7. We asked ourselves, what makes a good nucleophile? And we actually said there were 2 key components of a good nucleophile. The first is the presence of a charge. If I have an anion, and I'll just say like X negative, whatever X might be, that net charge makes a very good nucleophile. Now remember, a nucleophile seeks an electrophile. So this is my positive target, an electrophile. I want a nucleophile that's very negative because opposites attract. So if I have a negative charge, I can see that I will have a strong nucleophile. Here is hydroxide. Its conjugate acid would be water, HOH. Water is a weak nucleophile simply because it's lacking the negative charge. Weak nucleophiles will promote SN1 reactions, not SN2. And the second, and probably even more important, is the polarizability of that electron cloud. The ability of an atom to stabilize its negative charge over a larger surface area helps to create a more polarizable nucleophile. And we have to just remember the periodic trend of the size of atoms. As you go down a group, atoms get bigger. Iodide is a better nucleophile than bromide, who's a better nucleophile than chloride. Fluoride is so small, don't select it. Iodide has the ability to distribute the negative charge over a larger surface area than bromide, who can distribute it over a larger surface area than chloride. By the time I get so tiny with fluoride, it's too small, and it's not very good at stabilizing its extra negative charge. So increasing the size of the atom increases the nucleophilicity. Same over here in group 6A. Here's oxygen versus sulfur. Sulfur is a better nucleophile, carrying a negative charge over a larger surface area. These represent examples of strong nucleophiles and examples of weak nucleophiles. We really need to spend time understanding what makes a nucleophile strong so that I can predict an SN2 mechanism, or perhaps even an E2 mechanism when we get there, versus weak nucleophiles, which will promote E1, SN1 mechanisms. Notice these are protonated. The hydrogens are on an electronegative oxygen. Because I would also put something like RSH in this example as well, or HOS, something like that, where I could replace oxygen and sulfur. You could have H2S, you could have RSH, I got that up there. All right, so those are examples of weak nucleophiles. They're protonated. They have a hydrogen on their electronegative element. Notice over here in the strong nucleophiles, these all carry negative charges. So one of the conditions to recognize strong: iodide, bromide, chloride. You can see the negative charges. And I would rank these as being the strongest nucleophile, which is largest, to the weakest nucleophile, which is the smallest atom. It's still a strong nucleophile, this cyanide, because it carries a negative charge. But again, I would see the strongest nucleophile at this end, and then carrying over to this end. Here's sulfide listed before oxide, again based on size, and then the carbon, which is the smallest of all, still strong, but not as strong as you read from left to right. Strong nucleophiles favor bimolecular collisions. We also need to consider the solvent. For Sn2 E2 mechanisms, we must have a polar aprotic solvent. The solvent is necessary for reactions to occur. We understand that we cannot have dry ingredients and expect collisions. There has to be a way for molecules to move. That's the function of the solvent, allowing the kinetics to occur through kinetic molecular theory. The molecules move. Now, what kind of solvent would promote this mechanism? I want you to just consider the nucleophile for a moment, which we just said a good nucleophile carries a negative charge. If I had a protic solvent, something like water, for example, HOH, what you would notice is that this solvent is going to begin to just surround the nucleophile just based on polarity of the charge. And if I surround this nucleophile with the molecules of the solvent, how does that have the possibility of going to attack my electrophilic carbon? Right? I don't want it to have this big surrounding area of the solvent to create bulk and expect it to get in there to actually hit then on that carbon. So aprotic solvents are selected on purpose to keep the nucleophile naked. In other words, I want the nucleophile to not be surrounded by the solvent as a protonated solvent would do. Since protic solvents engage in hydrogen bonding, it would surround the nucleophile and actually prevent possible collisions, and that's what we're hoping to have in an Sn2. We need a collision to force the leaving group to leave. Aprotic solvents stabilize both cations and anions, but not through hydrogen bonding. So this is what we need to promote collisions. And the collision even for E2 for extracting the beta hydrogen, acetone, DMSO, which is dimethyl sulfoxide, acetonitrile, dimethylformamide, DMF, hexamethylphosphoramide, HMPA. I would say know these solvents. In other words, you need to recognize when you just see these letters if they are going to be protic or aprotic, because the selection of the solvent matters to promote Sn2 mechanisms. We need it to be aprotic. If I see DMF on an arrow, I need to know that's an aprotic solvent. HMPA, DMSO, all examples. And I don't necessarily need you to kind of envision the structure. It's not part of the actual mechanism, but it's there to help the mechanism be successful. So just to emphasize, aprotic solvents are necessary for Sn2. We want to keep the nucleophile naked. We do not want it to be surrounded through bonding from the solvent. DMSO is not a protic solvent. Therefore, it does not surround and make that nucleophile sterically inaccessible. We want that nucleophile to remain able to get to the electrophilic carbon for a collision. Let's take a quick checkpoint. Which of the following reactions are expected to produce 1-propanol at a faster rate? So notice what we're doing. We have a substitution reaction. Chloride turned to hydroxide. Chloride turned to hydroxide. So that's the same. Our base, NaOH, sodium hydroxide. Oh, here's the difference. DMSO versus water. Which one is going to promote the kinetics of Sn2 faster? Well, we just said we need an aprotic solvent. This occurs at a faster rate than if you had a protonated solvent. So we had a primary alkyl halide. We have the presence of a strong nucleophile. Those are all the same. The only difference in this question is the selection of the solvent. We want to select a polar aprotic solvent over a polar protic solvent, and that is this equation, number 2. Which of the following reactions is expected to exhibit a faster rate? Explain. Well, it looks like we're starting with the same alkyl halide. This is bromide, but I notice that we're switching bromide into iodide and bromide into chloride in this particular example. So the difference here is the nucleophile. In the first example, the nucleophile is the iodide ion, and in the second example, the nucleophile is the chloride ion. The iodide, with its larger electron cloud, more polarizable cloud, is the better, stronger nucleophile. Therefore, this would occur at a faster rate. Whoops, wrong one. Faster rate on the iodide. And that was that. Really just kind of reflecting about what makes a faster kinetics. And that is where we're going to stop for this lesson. Take a little break, come back, and we'll work on some more. Oh, you're doing great. I want to keep encouraging you. It's a long, tough chapter.